What's up, everyone, and welcome back to Access Point. In our last few videos, we laid down the groundwork. We talked about what databases are, how SQL works, and the different flavors of SQL injection. But theory is one thing, practice is another. Today, we're diving headfirst into the practical side of things right here in Vector Labs. We're going to take that error-based vulnerability we found earlier and walk through the entire exploitation process, step by step. And the best part? The methodology we use today will be the exact blueprint we adapt later for those trickier time-based and Boolean-based injections. So, here's our starting point. We know the vulnerable application has a table with 5 columns. The first thing any attacker wants to know is, who am I and where am I? In database terms, that means finding the current database user and the database name. To do that, we're going to use our error-based injection to sneak in a couple of useful functions, user and database. Let's craft our payloads. We'll fire them off, and boom. Just like that, the application spits back the info we need. We can see the current user and, more importantly, the database name. Perfect. Our foothold is established. Now that we have the database name, our next mission is to map it out. We need to find out what tables are stored inside flask_blog_app. We're basically looking for the treasure chests. To do this, we'll query the information_schema.tablesView, filtering for our specific database. And check that out. The query returns 2 tables, posts and users. While the posts table might have some interesting blog content, the users table is the real prize. That's almost certainly where the login credentials are stored. We found the treasure chest. Now we need to find the key. We know the table is called users, but what's inside? We need to find the column names to know what kind of data we can extract. Are we looking at usernames, emails, passwords? Let's find out. We'll use a similar payload, but this time we'll query information_schema.columns to get the column names from the users table. And there we have it. The table contains several columns, but the 2 we care about are right there, username and password. It doesn't get much clearer than that. We've confirmed the location of the credentials. All right, this is the moment we've been working towards. We know the database, the table, and the columns. It's time to dump the data. With our final payload, we're going to select the contents of the username and password columns from the users table. We send it off, and jackpot. We now have a list of all the usernames and their corresponding password data from the database. For demonstration purposes, I prepared a Python script that automatically sends this payload and parses the HTML code to extract the username-password pairs. Let's try it out. And there we have our users table dumped using an SQL injection attack. But hold on, we're not quite done. If you look closely at the passwords, they're not in plain text. They're a long string of characters. This is a password hash. Unfortunately for the application's users, this web app is using MD5, a very old and weak hashing algorithm. Crucially, it's also unsalted, meaning the same password will always result in the same hash. This is a huge security flaw and something you should never see in a modern application. This weakness allows us to use a technique called rainbow tables. Think of a rainbow table as a massive, pre-computed dictionary of hashes. Instead of taking a word, hashing it, and comparing it, we can just take the hash we found and look it up in the table to find the original password. We'll feed our list of capture hashes into a rainbow table cracker, and just like that, we start getting matches. We are now converting those seemingly random strings back into the original plaintext passwords. Game over. Now that we have the blog.admin plaintext password, we can test the login page. And there we have it. We are able to log in high-privileged parts of the application. So, what we just did was an error-based injection, which is fantastic when it works because the server literally hands you the data. But in the real world, most systems are configured not to spill their guts like that. This is where you'll run into blind SQL injection. The methodology is the same. find the database, tables, columns, then data, but the technique is completely different. Let's briefly touch on how we'd adapt our payloads. First up is Boolean-based. In this scenario, the application doesn't return data, but it does change its response depending on whether our query is true or false. So we can't ask, what is the table name? Instead, we have to ask a series of yes or no questions, one character at a time. For example, instead of dumping the table name, our payload would ask, is the first letter of the first username a? If the page loads normally, our answer is yes. If we get an error or a different page, the answer is no. Our payload first orders the user's table by their ID. So ID 1 goes first. Then we limit the search to only the first result, which in this case is blog page underscore admin. You can see how this would work. We'd have to script this to go through every letter and every character position to slowly spell out the table names, column names, and eventually the data itself. It's slow, but it gets the job done. But what if the page looks exactly the same, whether the answer is yes or no? This is the toughest scenario, and it calls for a time-based attack. Here, we can't even rely on a visual change on the page. Our only indicator is time itself. Our payload will be structured to tell the database. If the first letter of the first user's username is B, then sleep. The inner workings of this payload is pretty much the same as the Boolean-based one. First, we order the results by their ID. Then we limit to only get the first result. If the website suddenly hangs before loading, we know the answer to our question was yes. If it loads instantly, the answer was no. This is the ultimate brute force method for blind injections. And just like the Boolean method, it relies on automation to patiently extract the data, one character at a time. So as you can see, even when the injection is blind, the core logic of enumeration stays exactly the same. We just have to get a lot more creative with how we ask our questions. And that's the process. We went from a simple error message to dumping the entire user credential database and cracking the passwords. We identified the database, enumerated the tables and columns, extracted the data, and cracked the weak hashes. Now you have the core methodology. In our next video, we're going to see that the impact of an SQL injection attack can go much beyond of data exfiltration. Thanks for tuning in to Access Point. If you learned something today, make sure to hit that like button, subscribe, and ring the bell so you don't miss the next one. Drop any questions you have in the comments below. Stay safe out there, and I'll see you in the next lab.